So, yeah, as Luana said, my presentation will be a little bit more on the scientific side, on the regulations, and maybe to tell a little bit about the concerns about the regulations that have come up. So, for example, the Single-Use Plastic Directive, and also how we can respond to those regulations, but also some that are still coming up. So we all know that we have a huge problem, global challenge with plastic pollution and its accumulation in our environment. And despite the fact that there is a growing trend for circular economy, the recycling systems in many countries are not that efficient yet, and a large part is actually accumulated in the oceans and environment, causing serious ecological problems such as nano and microplastics. And thus we really need to kind of develop more sustainable material alternatives for plastics to at least partly replace them, and also to kind of provide tools how we can analyze the micro and nanoplastics that have been leaching out of these plastic materials. So today I will present you then two kind of cellulose-based solutions to these challenges. So the first one is a cellulose-based plastic alternative for plastics, and I will talk a little bit about this, how we can modify the biodegradability by controlled modification, and then the other part is related to this microplastic analytics. And I will start with the first one. So chemical modification of cellulose. So why is cellulose chemically modified? Of course, it's mostly to increase its solubility and also to make it more thermoformable, so similar to plastic materials, and also to increase its durability. However, we need to keep in mind that the modification will also affect the inherent properties of cellulose, for example, the biodegradability and also the mechanical strength that we really value in our bio-based material. So the question is, if we modify cellulose, does it then become a plastic? And at least according to this EU regulation, EU directive, which is the Single-Use Plastic Directive, that defines also modified natural polymers such as cellulose as a plastic. So it's only making a comparison between the natural polymer and then its modified counterpart. So it's not kind of looking into what extent it is modified and how it will really affect the inherent properties, for example, biodegradability, which is the main issue, of course, in the Single-Use Plastic Directive, that it's trying to kind of inhibit the accumulation of plastics in the environment because the plastics are not biodegradable. But the question really then comes to that, can we modify cellulose so that we can retain these inherent properties such as mechanical strength and especially biodegradability, so that we can tune the chemical structure but still retain the biodegradability and not compromise it? So I have here divided the chemical modification of cellulose into two routes, so the bulk chemical modification and then the surface chemical modification. In the bulk chemical modification, cellulose is basically dissolved into different solvents, and after that it is modified, or then it's modified simultaneously. But basically in the polymeric level, then cellulose is composed of these sugar units, and each of the sugar units has 3 hydroxyl groups which can be then replaced by these different substituents. So these are all cellulose derivatives you might be very familiar with, for example, with methyl cellulose or cellulose acetate, which is used, for example, in cigarette filters, or then eyeglass frames usually also are made of cellulose acetate. And then the degree of modification is generally defined as this degree of substitution. So it ranges between 0 to 3, depending on how many of these hydroxyl groups are changed. So the maximum is 3. And then to the surface chemical modification. So there we do not dissolve the cellulose fibers, but we actually do the chemical modification only on the surface of the fibers or fibrils, so that the inner part of the fibers remains unmodified. So here then the degree maximum degree of modification is only approximately 1, because if we go above that, it will start dissolving the cellulose fibers. So this already is a way to control the biodegradability. So how will this affect the chemical modification? How it will affect then the biodegradation? So here I have I will present now the bulk chemical modification. So we have prepared cellulose films from different cellulose derivatives, and they are in the figure there. And then we also have all the films on the graph. So we have done this enzymatic degradation test, which is basically a 2-day incubation with cellulose degrading enzymes. So it's a mixture that has enzymes that are also found in nature that are known to degrade cellulose. So we see that, for example, for regenerated cellulose, which is natural unmodified cellulose, it has a 100% degradation already in these 2 days. But then on the x-axis, where we have the degree of substitution, so the more we modify the cellulose, the more the kind of enzymatic degradation decreases. So basically this is because we have then these longer kind of substituent chains there, and it actually blocks the enzymes from attaching the polymer and breaking it down into these glucose units. And we see that there is a really exponential decrease, and the degradation is already clearly lowered at a degree of substitution of 1. So we really need to have fine control over the modification so that we're able to retain the biodegradability. So then to the controlled surface modification. So this is from a recent paper from Alistair King and others, where they did this controlled surface modification on cellulose nanopapers and papers. So basically you have a paper or nanopaper substrate, and then you put it into these acetylation reagents, and then you keep it at constant temperature. And the parameters or the variables that were changed here were the reaction time and then the volume percent of acetic anhydride, and the rest was then pyridine. So these represent now 9 different test points, and here we utilize this design of experiments to see how the variables will affect then the modification and also the biodegradation. So here is the NMR results from all these 9 different test points, so different reaction times and reagent concentrations. And from the peaks, we can calculate then the degree of substitution, which was the degree of modification. And we actually see that by controlling the reaction time and then the reagent, we can control the degree of modification. And really, with the mildest conditions where we do not have the pyridine, which is the catalyst in the reaction, we get still really low, we are able to reach very low values of degree of modification. And from these experiments, it's actually we are able to build up these models where we can actually also predict the degree of substitution and then the digestibility, meaning the degradation, also outside these reaction points, so we can actually see where we have the highest or lowest digestibility. So really the biodegradability can be also controlled on the surface. And here is the same NMR data for the 9 different test points. So from the same peaks, we can also calculate the percentage of the cellulose triacetate forming on the surface. And cellulose triacetate is kind of a similar that the commercial cellulose acetate is, so it's very resistant to biodegradation because it's all of the hydroxyl groups are modified there. And we see that with this three upper experimental test points, there is no cellulose triacetate formation. So the reaction is really occurring only on the surface of the fibrils. And here we can see that the similar enzymatic degradation tests, and we see also that when we have this very selective acetylation only on the surface chains and there is no cellulose triacetate forming, we still see the degradation in the 2 days. But when we start having these cellulose triacetate domains there, the degradation decreases. And of course, it will depend on if we have longer times. We could see more degradation, and also in different environments, because there are also esterases available to degrade cellulose acetate to some extent, but here we used only these cellulose degrading enzymes. But what is also important to note here, that even though this is from a natural origin, these cellulose triacetase is very resistant to the biodegradation and could actually be also a source of microplastics. So even though the other parts would degrade, it might be that these cellulose triacetate domains still remain and are causing the microplastics. And this brings then me to the next part of the presentation, which was then this microplastic analytics. So we have used these surface-sensitive methods together with cellulose to kind of analyze the microplastic capture. So the problem with microplastics is not only that they are everywhere, there is also a challenge in kind of analyzing and detecting the smallest fraction, so below the 1 micrometer, so the nanoplastic region. And there are really no tools currently to analyze these particles. And as there is more, we are becoming more and more aware of the microplastic accumulation, there will I'm certain that there will come some regulations also to measure and analyze the microplastics, for example, in process waters or in laundry waters or wherever we are kind of accumulating the microplastics. So we really need tools also to detect even the smallest fractions. So here we have combined these surface-sensitive methods with cellulose, and we have used this QCMD, which is basically a very sensitive balance that is able to measure the adsorbed mass of these nanoparticles on different surfaces. So basically you inject the nanoparticle solutions through the chamber, and then you measure the change in frequency. And the change in frequency is then the same as the adsorbed mass of the nanoparticles. So you can really calculate small amounts from low concentrations. And we have then combined this together with image analysis and modeling tools to kind of calculate the number of the adsorbed particles on these cellulose surfaces. So here you can see the QCMD results, and we see that there is this negative change in frequency, which indicated the absorption of the particles, and we see that RC, which is regenerated cellulose, absorbs the most of the particles. So it's very efficient in capturing the nanoplastics from the water. Then we have applied this image analysis using MATLAB to detect the different nanoparticles to be able to identify and also quantify then the amount on these different surfaces. And then we have evaluated the efficiency of these materials and compared it to this theoretical surface coverage maximum, which is based on this RSA model. So the maximum coverage is 50% of the surface, and with the regenerated cellulose we're able to only in a 1 hour test are able to reach already 50% coverage. So this really shows and validates that regenerated cellulose is very efficient in capturing the nanoplastic particles, and also kind of proves that it could really be used as a surface in analyzing and capturing the microplastics. So then to the conclusion. So cellulose really can be modified in a way that does not compromise its biodegradability. So even though we would have a modified cellulose, if we just control the degree of the modification, we're also still able to retain its biodegradability, and it won't accumulate in the oceans similar to the plastics. And of course, we need still, for these all different materials, further analysis also in different type of environments if there is a risk that they are lost in the environment, so that they really degrade also there. And then to this analytical side, so this interfacial approach could be really used together with this regenerated cellulose to analyze different nanoplastic waters. So we have validated the system now with kind of this model system, and the next step is really to start also analyzing real waters, real process waters. And this could, for example, also be further coupled with this infrared spectroscopy to really also get the chemical identity of the different particles. So here we use polystyrene as a model particle, but if we want to see what type of particles that are absorbing, we have tools also to get the chemical identity. Thank you.
Thank you, Ilona. It's a quick question. I was wondering, for these modifications that you identified that can biodegrade, what would be the main applications? Because there's always this balance between the performance that the different applications require and the possibility to make the biodegradable material. So have you thought about what applications fulfill?
So where you still see some biodegradation, did you mean those?
For the biodegradable modified,
yeah.
What would be the main applications?
Yeah, well, I think, for example, if there is these single-use plastic items that they have identified that have a very high risk in ending up in the environment, so those are also the single-use. They're, of course, not used for a long time, so they don't need that same durability, for example, as plastics. And then, of course, if they're made of these modified papers, they could be recycled, but if they end up in the oceans and environment, they would degrade then there after a certain time.
Perfect and wonderful. Maybe one quick question from the audience. Erfan?
Thanks for the nice presentation. I would like to know what is your opinion about this controlled surface modification on the recyclability of nanopapers?
Well, that is something we have not tested, but I think also there it depends on the degree, how much it is modified, because of course you can recycle in the recycling streams also kind of multi-materials, that because there can be a certain amount of, for example, reject and so on in the paper recycling as well. But also I think that will also depend on the degree of modification. Of course, cellulose acetate is not recyclable in paper stream, so that also depends on really how we modify it and to what extent.
Thank you.
Thank you so much, Ilona, and another round of applause.